So welcome back to the second half of the chapter 13 notes covering free energy, entropy, and we'll relate all three, entropy, enthalpy, and free energy together. So, and we'll also talk about how the free energy is similar to, or is at least reflected in, the equilibrium system. Okay, so Gibbs-Helmholtz equation, actually you're already familiar with this. We talked about this last year, but the Gibbs equation is delta G equals delta H minus T delta S. Of course, in advanced or pre-AP, we had you guys memorize this formula. We did it as guys are hot minus without their socks. At least that's the appropriate way to do it. And that's fine, but you guys don't have to memorize it in AP. In AP, it'll be on your formula chart in the thermodynamics section. There is an additional formula, which we'll talk about in a little bit. It also is on your formula chart. So as far as the Gibbs free energy questions, you know, they're pretty straightforward. You do need to make sure that you are in kilojoules in order to solve these problems. And we'll go through and do a few of them together. So, or at least one together. So for the given reaction of the following information, calculate delta G for this. And they give you a series of data here for your enthalpy, your delta H values, and your entropy, which are your delta S values. Notice there is a unit difference between the two. You know, you could do this a couple of different ways. You could solve it all and then go change the units before you put it into Gibbs-Helmholtz, or you could change it all right now and then do it. It doesn't really matter. One little hiccup here is this question mark right here. And so, you know, well, what is the value of oxygen in its standard state for enthalpy? And the answer is 0. What we're really doing there is just reminding you that things that are in their standard state or elements that are by themselves, remember the H-bond cliffs will dimerize and form O2, H2, N2, and so forth. But those values will actually be 0. So what it's having you do is calculate, and I'll just show you this really quickly, but the delta H will be the delta H values for the products, the formation values for the products, minus delta H formation values for the reactants. And so you'll just take the sum of the products multiplied by their coefficients and the sum of the reactants multiplied by their coefficients, and then solve. You'll do the same thing with the delta S values. Remember that your delta S values are going to be given in joules, but you'll just do the delta S values of the products, you know, minus the sum of the delta S values for your reactants, and you'll get your total delta S value for this particular reaction. So I've done that here down there at the bottom, and you can see I get, you know, 830 kilojoules per mole of the reaction above, and then 161 joules per mole Kelvin for the reaction above. You do need to change your S values, your entropy values to kilojoules before you plug into Gibbs-Helmholtz. So I've done that here. I would take both this delta H and delta S and plug into the calculation. They did tell us that the temperature was 25 degrees C. So that's, you know, you just change to Kelvin by adding 273. And there's your final answer there, having plugged into the equation. If you need to pause. I'm going to keep going, but this is a straightforward problem. It's likely that you would see this in several steps, right? You would be calculating your enthalpy value, calculating your entropy value, plugging in to solve for your free energy. In this case, it says 782 kilojoules per mole reaction. I kind of want to just talk a little bit about that. This part down here, that means that it still needs energy in order for this reaction to occur without outside intervention. So in other words, it won't occur without outside intervention. This is it's kind of a dead giveaway if you look at the delta H value here. The delta H value up at the top is 830 kilojoules per mole. If you look at your S value, it's positive 0.161 kilojoules per mole, which is a really small number. But when you multiply that by 273, you might be able to see that as you increased that value, the value for delta G is going to become more negative. And that's key, you know, so at higher temperatures, meaning significantly higher than 25 degrees C, you would start to see this reaction become spontaneous. The reason being that you are putting more energy into it. This is an endothermic reaction, right? Because it's positive delta or positive 830. So that 830 kilojoules would be written on this side of the equation. That being true, As you input energy, it would shift to the right to form more products, meaning that as you increase the temperature, you are actually going to make it more spontaneous. So that hopefully will bring into play here, or into your mind at least, the combination of things that we've discussed. We have discussed Le Chatelier's principle and shifting the equilibrium based on certain things. We've talked about endothermic and exothermic reactions, and now we're talking about the thermodynamic favorability of these reactions at different temperatures. And in this case, at a higher temperature, this might actually cross that threshold and become spontaneous, which is interesting. Just thought I would share that information with you since we're doing notes, but okay. So the dependence, of free energy on pressure. So entropy and pressure, the pressure, with pressure changes, you're actually going to change your entropy values. Now, we're going to treat most of these under standard conditions of 1 atmosphere of pressure and 25 degrees C, but if those things change, it actually changes your entropy values. So if you increase the volume, give them more space to spread out, that pressure will actually go down and your entropy value would actually increase. That would give more opportunity, or the probability would be greater for them to be in a more of a disordered system, or more positional probability is another way of saying that. Same thing would be true as if you raise the temperature. If you raise the temperature, you're going to change that entropy as well. And so that's going to have an effect on your delta G. However, most of the time, we're not going to be manipulating that kind of stuff. That would be more of a theory-based question. Numerically, we're going to stick with those that are at standard values of 1 atmosphere and 25 degrees C. If you do incorporate Puvnert into your equation for Gibbs-Helmholtz, you can come up with an equation, which I'm not going to derive for you, but an equation here where you can find what happens to delta G as a result of not being at equilibrium, or as a result of whatever pressures that you're starting with, gases only, that you're starting with in the equation. So since you don't know if you're at equilibrium, we've substituted in Q here. So the formula is delta G equals delta G naught plus RTL in Q. And in this particular case, you could go and solve for what change in delta G would be from its standard delta G based on new concentrations added to the system, or concentrations you know or may not know are at equilibrium. And so you could calculate. If your delta G's end up being the same, then of course you're at equilibrium, but we'll go and do that in a minute. Temperature has to be in Kelvin. The R value here is, of course, your energy R value of 8.314 joules per mole K, or 8.3145 is fine. Your delta G naught is going to be at 1 atmosphere. So make sure we're using joules for this. A lot of you may want to put in your liter atmosphere mole Kelvin like you do in Puvnert, but that's not what this equation is asking. We're looking for joules. So let's do an example here. So it says calculate delta G at 25 degrees C, 298 for the following reaction if the mixture consists of 1 atmosphere of nitrogen, 3 atmospheres of hydrogen, and 1 atmosphere of ammonia. So you know the partial pressure of all the gases present. You're going to have to go set up a Q value here because you don't know if this is an equilibrium. So you set up the Q expression just like you would an equilibrium expression. And so in here for Q, I'm going to be putting my ammonia, wouldn't be concentration, partial pressure divided by the partial pressure of my nitrogen, multiplied times the partial pressure of my hydrogen. And the hydrogen would be cubed due to its coefficient, and the partial pressure of the N3, tolerant, really? Not sure what that is really. Of the NH3 would actually be squared as well. So you'll plug those values in, meaning your 1 atmosphere of NH3, your 3 atmospheres of hydrogen, and your 1 atmosphere of the nitrogen into that equation to solve for Q, and then put that into the actual equation. Your delta G value would have to be given to you in this case, and it is negative 33.32. And so you plug in your R value of 8.3145 and your temperature. One hiccup though, the R value is 8.315 joules per mole K, and your delta G is given in kilojoules. You've got to change one of the two of them. I tend to change my delta G value to joules and then go solve, but you could do either. Either should work, whether you change it to joules or kilojoules, but you've got to make sure both of them are in the same unit. So if I were to plug that Q expression in here and solve, I end up getting about negative 41,500 joules per mole. Now that is in joules. They didn't specify whether they wanted it in kilojoules. It is customary to put delta G and delta H values in kilojoules per mole, but it wouldn't really matter if they didn't ask. And I wouldn't mind which one you put them in either. But yeah, kilojoules per mole be negative 41.5. So free energy in the equilibrium. So far that last one, I should say, that last equation is you're not at equilibrium, or we didn't know if we were at equilibrium. If you know you're at equilibrium, then the delta G in that previous equation is actually 0. So what would happen is your RTL and K would be the same value as your standard delta G value, and those two combined would end up giving you a value of 0, and so your delta G would be 0. In a phase change, which I mentioned on the previous video, in a phase change, your delta G is always 0. And so you can just plug that in and solve those. So anyway, moving on, the equilibrium point is the point at which that free energy is the minimum that you could use. If it shifted to one side or the other, if you've got more products or more reactants, there's going to be some differences in what you're actually going to get. And your delta G is either going to be too high or too low as a result. But the minimum amount of free energy is where that equilibrium point rests. So, and it's the same formula that we're using, but you need to know that the delta G value would actually be 0. So if you have your delta G of your products and delta G of your reactants actually equal to 0, then what it is right then is you are at equilibrium. Now, this is not necessarily true for delta G naught. It depends. If your K value is 1, then yes, your standard enthalpy change or your standard Gibbs free energy change would be 0. But here it's talking about your change in delta G. If it is 0, you can actually go solve for where the phase change occurs. In other words, you could solve for your boiling or your freezing point. Yeah. So if I look here, really boiling point, but if I look at it here, I've got given for the reaction of mercury as a liquid going to a gas. So basically the boiling point of mercury as a liquid going to a gas. The delta H and delta S values are given to you. It says calculate the temperature of the normal boiling point for mercury. So the delta G value here is actually 0 because it's in a phase change. And so if that's true, I can rearrange this equation to be delta H equals T delta S. All I did was move this term over to the other side, right? And so I've got my delta H equal to T delta S. I could divide this side by delta S, get rid of my entropy value, and I would have the temperature at which the liquid goes to the gas, which is the boiling point. So a quick and easy way to solve for boiling point. This question often shows up in multiple choice on your AP exam. I don't know that it would necessarily show up in the free response, but it could. But you would definitely see something like this in the multiple choice. Quick, easy problem to solve. Not necessary that you have a calculator, really. Definitely kind of a multiple choice type question. But plugging in the numbers, you end up getting about 603 K. They didn't ask for the degrees Celsius, so it's fine to leave it 613 K, but I don't know if for you, I don't think that's really relevant. Degrees Celsius or something that is more tangible, but it doesn't matter. Either one would be fine. In fact, if they don't specify, I would stop where you can before you make yet another mistake. So just write 613K. So the last one is where the last formula for us to discuss is going to be if delta G is 0. So if you're at equilibrium, the delta G change here, if this value right here is actually at equilibrium, then that is your K value. If that's true, then this delta G value here is 0. If I rearrange the equation and move this term with the RTL and K to the other side, I end up with what we call the Ratlink equation. Now, the reason we call it Ratlink is because they had to memorize it in the old days for multiple choice. You guys don't have to do that. And this formula is actually on your formula chart as well. And so if delta G is 0, then, you can go and solve this for delta G based on K or find K. And you could find K from, if you were given delta G. More often than not, there'll be plug and play questions like this, but they might ask you sort of a Le Chatelier question about this. If they give you the K value or they give you the delta G value, well, what would happen? Which way would it shift, right, left? Or what's favored, the reactants or the products at equilibrium? They could ask you questions like that. If you're given K values, it's really simple. If K is greater than 1, that means the numerator of K, which is products, well, which is, products divided by reactants is how K is set up, then you would know if it's greater than 1 that you have more products. Well, if the K value is greater than 1, then your delta G is actually going to be negative. So if you end up with a negative delta G, you already know that it's going to favor the products. And so if delta G is less than 0, or it's negative value, then your K value is going to be greater than 1. If your K value is less than 1, then your delta G value is going to be positive, which means that it's not spontaneous or is not thermodynamically favorable. Also, the K value is favoring the reactants, which means not as many products are formed. And so that's that favorability again. And so you can see relationships asked. You'll have theory questions asked about just straight up from this equation. You can use this equation to understand those things if you understand logs. And we'll go through and do a few questions in the homework over that to help you. But just looking at this right here, it says calculate the approximate standard free energy for the ionization of hydrofluoric. The K value is 0.001 or 1 times 10 to the minus 3. If that's the case, you should already know that delta G is going to be positive. But you could go, of course, and calculate it. Your delta G naught value is going to equal negative RT ln K. If you plug in your R value as 8.3145 and your T value here is 298, you can take the natural log of 0.001 or 1 times 10 to the negative 3 and go solve this equation. You're going to get a positive value for delta G. If I go down here and look at the equation, sure enough, 17 kilojoules. It's pretty high. So this is not favorable, which makes sense. Your K value is favoring the reactant side of the equation, not the product side of the equation. However, ionization of hydrofluoric acid is HF is going to H plus F minus. That's actually increasing in entropy. So the higher the temperature value that you add here, you can make it actually more favorable. So it would probably be an endothermic reaction. It's definitely an endothermic reaction. But anyway, if you can interrelate those kind of things in your mind and be able to think through them, it'll make a big difference, especially in the multiple choice. So last is kind of summary, same thing. Using this equation, which, by the way, is not found on your formula chart. We'll do some homework questions over it. I might ask you a question on your exam with me, but I think you're unlikely to see a question about this on your AP exam without them giving you the formula. But if you don't know you're at equilibrium, you have to use this equation to find out where you are in relation to equilibrium. So what is this delta G essentially? I talked a little bit about it before, but delta G really is the amount of energy available to do work. If you have a negative value for delta G, it's a lot like an exothermic reaction with a negative value for delta H. There's energy given off in the reaction with delta H. Well, with delta G, what you're finding is that there is actually energy left over after the reaction occurs, which means that it is favorable. It doesn't require more energy. There's extra energy left over, so the reaction continues to happen, which actually makes it spontaneous. So what we're saying is the amount of work that can be done is directly related to what that delta G value is. If that value is positive, then there's not enough work to complete additional reactions and more work is necessary. If that value is negative, then there is additional energy for work to be done and the reactions continue and in fact are spontaneous. So that kind of concludes what we're talking about here. There's the bell. So if you have questions, again, talk to your instructor. You guys should be in good shape. And okay, there you go. There's chapter 17. Thanks. Jody Slaughter, Dawson Deere, and